My name is Ashwin Kambhampati, and I'm going to talk to you today about robust performance evaluation. So this paper is concerned with a very simple and classic incentive problem of the form displayed in the following infographic. Here we have a principal, I'll call her Clara, who oversees and compensates two sales agents, Alice and Bob. Alice and Bob each can take a costly but unobservable action, which map into different probabilities with which they make a sale. Check indicating making a sale, X indicating no sale. Clara, unable to observe the actions that Alice and Bob took, designs a contract that maps these success and failures at completing a sale into a compensation or wage payment to Alice and Bob. A classic question in this environment is what form should Clara's optimal compensation scheme take if she wants to maximize her profits? In particular, is it the case that Alice's payments should be linked to Bob's sales performance, or should Alice be compensated based on her own observable performance alone? Well, this problem actually already has a solution if Clara knows exactly what Alice and Bob can do. In particular, Holmstrom's classic paper in Moral Hazard in Teams says that if Alice and Bob are independent, in the sense that Alice cannot affect Bob's sales productivity directly, and moreover, if their performances are uncorrelated, conditional on the actions they take, then there always exists an optimal compensation scheme exhibiting independent performance evaluation. For instance, a scheme in which Alice is paid solely based on her own observable performance. But what if, perhaps truer to many real-life contracting situations, Clara only has a hazy idea about what Alice and Bob can do? For instance, she might know that they can slack off before meeting a client or lean forward to do firsthand research about them. But she's concerned about other shortcuts these sales representatives could take. For instance, they could call up a friend to learn about the client they're about to meet. This might be tempting to Alice if it's less costly in terms of her effort, but it might damage the performance of the contract that Clara offers if it's a less productive sales tactic. In the face of this type of uncertainty, Clara might write a contract to solve the following max-min optimization problem, where the max here is taken over contracts and the min is taken over other actions which might be available to the agents. I'm going to be in a world in which Clara evaluates her payoff by assuming that the agents will play a Nash equilibrium given the availability of these other actions. And I'll call any solution to this program a worst case optimal contract. This paper has exactly one theorem, and it's given in this slide. Basically, in a model very similar to the infographic I displayed, in which all parties are risk neutral, the agents are protected by limited liability, and the principal is constrained to use symmetric contracts, or contracts that respect equal treatment of equals. I'll prove that in any worst case optimal contract, individual wages possess two important properties. First, they exhibit joint performance evaluation. Alice's wages actually increase in the performance of Bob. And moreover, they are nonlinear. Wages are not a simple constant fraction of the total output produced in the firm. Finally, there exists a worst case optimal contract so that the properties I've just described to you are not vacuous. My goal in this talk is modest, so I'm only going to show you today, via a simple example, why nonlinear joint performance evaluation outperforms a contract you might expect to do well, independent performance evaluation. This is useful not only in contrast to the Holmstrom benchmark, which I described earlier, but also in contrast to a recent literature in robust contracting. In particular, Gabriel Carroll considers an environment similar to mine with a single agent and shows that independent contracts that are linear in individual output have good performance. Those arguments will extend to my setting because the principal will hypothesize that the agents are independent. And so independent performance evaluation will actually have very good worst case performance guarantees. At the same time, I'm going to show that one can do better with the second agent by linking the payments of the two agents. Right? The second reason to highlight this comparison is that nonlinear joint performance evaluation actually offers no worst case guarantees in settings in which agents can harm one another through their actions. In particular, Dai and Toika show that the existence of prisoner's dilemma type games yield essentially any contract that is not linear in output a payoff guarantee of 0. So the takeaway of this paper from a modeling point of view is going to be that robust contracting with bounded uncertainty really can yield new insights into classic incentive problems. In the language of robust optimization, the modeler's choice of uncertainty set is quite important in terms of its predictions for optimal contract form with worst case objectives. All right, so without further ado, let me get to the example. Let's fill out some details from the infographic I showed earlier. So Alice and Bob can either succeed, make a sale, or fail. Success will be valued by the principal at 1, and failure will be valued by the principal at 0. There'll be a single action that is known to the principal, work, and this will result in successful completion of each of these tasks with probability 1, and it will have an effort cost of 1/4. For the purposes of this example, I'll assume actually that the principal knows that there's exactly one other action that the agents can take. I'll call it shirk. She knows that this action has no effort cost, but she won't know the precise productivity of this action. In particular, its success probability, P star, will be something she's ambiguity averse over. In the general model, I consider the case where there's any set of known actions and there's any set of unknown actions, and I'll discuss that case briefly after the example. So how do we mechanically compute principal's max payoff guarantee from a given contract, all right? So the principal is going to commit to a mapping from success failure pairs into a real number. I'll assume that this real number is positive to reflect limited liability constraints on behalf of the agents. This will prevent selling the firm as being an optimal contract. And given that contract, we can compute a payoff given a shirking known value of given a value of P star as follows. So in particular, given a contract W and a value P star, the principal hypothesizes that the agents play a Nash equilibrium. One detail here, when there's multiplicity, I'll assume that agents can coordinate on one that's not Pareto dominated. But within this set, the principal is pessimistic. So she'll assume that the agents play the worst possible Pareto efficient Nash equilibrium. Right? Now we've associated for each contract W and each value of P star a numerical payoff for the principal. How do we find the worst case payoff of the principal for the given contract? Well, we just find the worst value of P star. Right? So let's see how this works in the very simple independent performance evaluation contract. All right. So suppose Alice and Bob each receive a payment of 0 when they fail at their making a sale, and they receive a wage of 1/2 when they succeed at making a sale. And importantly, this 1/2 that they get paid is unconditional on what the other agent's success or failure is. All right. This contract induces the following game between Alice and Bob for a given value of P star, depicted in the bottom left here. This is not really a game, all right? We see that Alice's action, due to the independence between Alice and Bob, is not affected. Alice's payoff from any action is not affected by Bob's action, okay? In particular, she obtains a payoff of 1/4 when she works, regardless of what Bob does, and a payoff of P star times 1/2 when she shirks, regardless of what Bob does. This means that if P star is less than 1/2, in particular, if the shirking action is sufficiently unproductive, then work is the unique Nash equilibrium. In this equilibrium, the principal Clara obtains a payoff of 1 minus 1/2. On the other hand, if shirking is sufficiently productive, then it tempts Alice and Bob to take this action shirk. Right? In this case, the principal's payoff will depend on the precise value of P star. In particular, expected output per agent is given by P star, and expected wages per agent is given by P star times 1/2. What does this translate in terms of the principal's payoff? Well, in this picture, we have on the y-axis the principal's expected payoff. On the x-axis, we have the value of this shirking parameter, p star. When p star is less than a half, the principal obtains 1/2. We go along this top line corresponding to the situation in which both agents work. But exactly at 1/2, agents now have an incentive to shirk, reducing their payoff to this black dot and the associated value on the y-axis. Clearly, in that equilibrium, when p star increases, the principal does better, okay? Because intuitively, when shirking is not so unproductive, she's not as harmed by it. But we see here that the worst case is obtained exactly when p star is equal to 1/2. Now, the beauty of Carroll's paper is that this is quite a good payoff for the principal, despite the fact that we're in a setting in which the principal doesn't know exactly what the agents can and cannot do. We do know that they're going to respond to incentives. And so agents will not be willing to shirk if the productivity of this shirking action is too low, all right? This paper is going to show that we can retain many of the properties of this optimal independent contract by constructing a team contract. But this team contract will do even better because in scenarios in which agents shirk, the principal will be able to reduce her expected wage payments. So let's see this practically. Let's consider the following perturbation of the optimal Carroll contract. Once again, we pay agent 0 for failure. Once again, we pay them 1/2 when both succeed. But now we reduce Alice's payment when she succeeds and Bob fails by a small amount epsilon, where actually epsilon can be anywhere between 0 and 1/2. This contract has an important property. I'll say it's calibrated to the benchmark independent contract W star, as well as the known action of Bob work. What do I mean by this? I mean that Alice's expected wage, conditional on Bob working and conditional on her working, is exactly the same as in the independent performance evaluation contract. The displayed equation makes this concrete. So we're taking a weighted average of W11 and W10. But when Bob works, he makes a sale with probability 1. Recall our parametric assumptions in this example. So that Alice's expected wage when working, in which case she gets W11 with probability 1, is exactly 1/2, just as before. Why does this property matter? Let's now look at the new game, which is actually a game because Bob's actions do influence what Alice gets paid, right? Well, we've retained many properties of the optimal Carroll contract, okay? In particular, when Bob works, Alice still gets a quarter when she works. When Bob works, Alice still gets p star times 1/2 when she shirks. So this means that when p star is less than 1/2, work is once again a Nash equilibrium. It's in fact the unique Pareto efficient Nash equilibrium because this is a game of strategic complements between Alice and Bob. However, in the scenario in which p star is greater than 1/2, once again, shirk is a Nash equilibrium. But the important point, in this equilibrium, Alice gets paid less than expectation. Why is that? We're now taking a weighted average of 1/2 and a number less than 1/2, which is obviously strictly smaller than 1/2, leading to a strict jump in the principal's payoff. Let's look at this graphically. When p star is less than 1/2, the principal gets paid the same that she did under the independent performance evaluation contract. But now when p star is equal to 1/2, or a little bit more than 1/2, the principal's payoff actually jumps relative to what she gets under independent performance evaluation. This is a consequence of the fact that team-based compensation enables her to lower her payments in these scenarios in which the agents shirk. So this is a clean example, precisely because agents have exactly one unknown action. In particular, I've illustrated a rent benefit of joint performance evaluation while holding efficiency cost constant through this calibration exercise. It turns out that with many unknown actions, this calibration will not ensure that efficiency costs are eliminated completely. In particular, I exhibit an n sequence of dominant solvable games with n unknown actions in which agents take less and less costly and less productive actions as dominated strategies are eliminated. I show that the worst case payoff for the principal is actually attained in the limit of this sequence as n approaches to infinity. Nevertheless, if we choose the reduction that Alice gets paid when she succeeds and Bob fails, judiciously smaller, meaning not too much smaller, we can show that the rent benefit of the example, the reduction in expected wage payments when agents shirk, strictly dominates any efficiency costs in any of these more general games that the agents might be playing. So let me wrap up this talk. So what do I do in this paper? I consider a robust contracting problem in which the principal knows the agents she compensates are independent. I show that in any worst case optimal contract, individual wages are both nonlinear and exhibit joint performance evaluation. This yields a new prediction, which hasn't been observed in the literature previously, which is that interdependent incentives might actually have value absent task interdependency and correlation in performances. This has the potential to shed light on puzzling incentive schemes observed in practice, where we see group compensation for co-acting groups. It also sheds light on a new mechanism, which is that joint incentives, in contrast to the conventional wisdom where we think that team-based pay is good because when Alice does well, Bob gets paid more, the opposite is just true. In the scenarios in which both the agents shirk, the principal is able to reduce expected wage payments to the agents. Put differently, joint performance evaluation flexibly adapts wage payments to agents' unknown environment and the equilibrium that they play. I leave this asterisk new. I put an asterisk next to the second new because this aspect of interdependent schemes has actually been previously observed in a paper by Nailbuff and Stiglitz in the 1980s. They write, the incentive compensation scheme that is correct in one situation will not in general be correct in another. The lack of flexibility of the piece rate system is widely viewed to be its critical shortcoming. Joint performance evaluation in this model has precisely the right flexibility to guarantee the principal good performance. Thank you very much for your attention and for watching my talk.